Somewhere in the darkness between stars, an object older than humanity's understanding of time itself just arrived at our doorstep. It carries a message written in molecules. The James Webb Space Telescope decoded that message in December 2025. What it found chemical ingredients necessary for life exist elsewhere in the galaxy, and this ancient visitor is broadcasting evidence that we're not alone. What comes next will reshape how we understand our place in the universe. Astronomers have a problem they're not talking about directly. They're trained to deal in facts, measurements, and peer-reviewed certainties. But last June, when the data from James Webb came back, when the spectrograph readings were analyzed and cross-referenced with ground-based telescopes across Europe, something happened that doesn't fit into conventional scientific discourse. The problem is this: we found something that shouldn't exist, traveling toward us from a place we've never been, and it's been moving toward us for over 10 billion years. It arrived on our cosmic doorstep last year, and we're only now beginning to understand what it means. On July 1st, 2025, the Atlas Survey Telescope in Chile detected something unusual passing through our solar system. The detection seemed routine at first. Thousands of objects drift through space. Most burn up or pass silently into the void. But this object was different. It was an interstellar visitor, one of only 3 ever confirmed. The first was discovered in 2017 called Oumuamua. The second came in 2019, Borisov. Now there was a third. The astronomical community recognized the significance immediately. Within days, observatories worldwide had locked onto it. Hubble pivoted. SphereX turned its instruments. Webb, the most powerful telescope humanity has ever built, would soon focus its infrared vision on this ancient interloper. What they were about to discover would fundamentally challenge how we think about the distribution of life's building blocks across the galaxy. The object is called 3I Atlas. The designation itself tells you everything about how the scientific community functions. 3 means it's the third interstellar comet confirmed to originate from beyond our solar system. The designation matters because when an object is confirmed to come from another star system, it becomes evidence of something scientists have theorized but never directly observed. It's a sample from another world, millions of miles away, billions of years old. Atlas refers to the survey that first spotted it, the Asteroid Terrestrial Impact Last Alert System. But here's what most people don't realize. Interstellar comets are not anomalies. They are, according to calculations that shocked researchers when they were first published, incredibly common. Our galaxy is full of them. They're constantly being ejected from young stellar systems, wandering the void in perpetuity. Most of them will never pass close enough to any star for us to detect. But this one did, and it was close enough for us to study. The journey to this moment began long before July 2025. The comet has been traveling through the galaxy for approximately 10 to 12 billion years. Let that number settle for a moment. The universe itself is only 13.8 billion years old. This object formed when the universe was barely more than 1 billion years old, during what astronomers call cosmic noon, the era when star formation reached its absolute peak. It formed in a stellar nursery so cold and so distant that the chemistry locked inside its nucleus preserves a record from the early galaxy that no telescope could ever directly observe. It is, in essence, a time capsule from the epoch when the universe was young, violent, and teeming with formation. The probability of this object existing, of it being ejected from its birth system, of it acquiring just the right velocity to intersect with our solar system billions of years later, is almost incomprehensibly small. Yet here it was, crossing into our cosmic neighborhood, bringing its cargo of ancient secrets. When James Webb first observed 3I Atlas in August 2025, using its near-infrared spectrograph, the data surprised everyone involved. Webb can't just take pictures. It analyzes light at molecular resolution. It breaks down radiation into its component wavelengths, and from that signature, contained elements and chemical ratios that had never been found in any comet within our solar system. The abundance of deuterium, heavy hydrogen with an extra neutron in its nucleus, was extraordinarily high. The ratio of carbon-13 to carbon-12 was unusually low. These isotopic signatures are like a genetic code. They tell scientists where an object formed and under what conditions. They become a story of temperature, of available radiation, of the metallicity of the stellar environment. And this story pointed somewhere unexpected. According to Martin Cordner, lead astrochemist on the study published in Nature on June 22, 2026, the comet's chemical composition suggested it formed in an exceptionally cold region, far from any star's warmth. The deuterium enrichment specifically indicates that the object spent time in an environment so cold that deuterium preferentially accumulated in ice. This only happens in the deepest, most frigid molecular clouds, where radiation from nearby stars is scarce, but cosmic rays are abundant. The implications are significant. If this ancient comet formed in such a cold nursery, then the birthplace was likely a region of intense planet formation, exactly the kind of environment where planetary systems emerge from stellar dust. The comet was essentially a refugee from a planetary system born during the universe's most productive era for star and planet creation. But the real breakthrough came when the data revealed something more. Alongside the unusual isotopic signatures, Webb detected the presence of cyanide molecules in the comet's coma, the glowing envelope of gas that forms when the comet is warmed by the sun. Cyanide sounds toxic, dangerous, but in the context of astrochemistry, it's one of the most important signals astronomers can detect. Cyanide is a precursor to amino acids, the fundamental building blocks of proteins. Proteins are the machinery of life. Cyanide alone doesn't mean life exists on this comet. Far from it. But it means something perhaps more important. The chemical precursors necessary for life to emerge are present in objects that drift between stars. This is not a discovery that life exists elsewhere. It's a discovery that the chemistry of life, the prebiotic chemistry, is ubiquitous in the galaxy. Raise is not whether this comet carries life. It doesn't. What the question becomes is how common are these conditions? If an object that formed 10 billion years ago in a stellar nursery on the opposite side of the galaxy contains the chemical building blocks of life, then how extraordinary is Earth, really? How many other worlds have received similar bombardments of prebiotic chemistry from interstellar visitors? How many planetary systems contain comets like this one? The analysis of 3I Atlas becomes a Rosetta stone for understanding whether the conditions that led to life on Earth are rare cosmic accidents or inevitable consequences of how the universe constructs itself. The comet's velocity adds another layer of significance that researchers are beginning to fully articulate. It's traveling at approximately 60 kilometers per second relative to our Sun, making it the fastest of the 3 known interstellar comets. At this velocity, it will never return to its birth system. It's on a hyperbolic trajectory that will carry it into the interstellar void forever. This means the comet is not an anomaly passing through temporarily. It's representative of something fundamental, a continuous, perhaps eternal exchange of material between stellar systems through the medium of these fast-moving objects. Every star system is potentially seeding others with the chemical building blocks of life. There's a cosmic distribution mechanism operating at the galactic scale that we're only now beginning to understand and measure. Maintains pockets of liquid where microorganisms could theoretically survive. Then this comet's passage would have bathed the entire planetary system in prebiotic molecules. The comet reached its closest approach to the Sun on October 29, 2025, coming within 1.357 astronomical units of the Sun's surface. At that point, what the spectrograph recorded was extraordinary for its ordinariness. The molecules weren't exotic or impossible. They were, in fact, exactly what we would expect from objects in our own solar system. But with one critical difference. The isotopic ratios were wrong for our solar system. They matched instead a different stellar environment, a different history, a different origin point in space and time. This is how astronomers confirmed the comet's alien ancestry. It wasn't that the molecules were unique, it was that the ratios told a story no solar system comet could tell. The comet was literally carrying evidence of life's chemical precursors from a world humanity will never visit, produced in an environment that no longer exists, traveling toward us as a messenger from the early universe. Complementary observations using the European Southern Observatory's Very Large Telescope added another dimension to Webb's findings. Astronomer Cyrielle Opetom led a team that analyzed the carbon and nitrogen isotopes, specifically in the cyanide molecules released by the comet. The results independently confirmed Webb's conclusions, while providing evidence of chemical complexity beyond what the Space Telescope alone could resolve. The presence of cyanide with specific isotopic signatures meant that the comet didn't just contain organic precursors. It contained organic molecules that formed through complex chemistry in a low-temperature, radiation-rich environment. The chemistry was ancient, it was sophisticated, and it was undeniably consistent with what we understand about how life's building blocks are assembled in space. The scientific literature is now asking questions that sound like they belong in science fiction. If prebiotic chemistry is this common in objects transiting between star systems, how many comets like this one have impacted Earth throughout its history? How many have impacted other potentially habitable worlds? If the chemical precursors for life are being continuously distributed across the galaxy by interstellar objects, does that change our assessment of how likely life is to emerge elsewhere? Does it suggest that the chemical foundations for life's emergence are not rare accidents, but inevitable outcomes of how the universe evolves? These are not questions with answers yet, but they're questions that couldn't be asked without the data from 3I Atlas. The discovery has geopolitical implications that extend far beyond astronomy. Nations around the world are now investing heavily in observational capabilities designed to detect and study interstellar objects before they pass close to Earth. The data that could be gathered from such objects would fundamentally reshape our understanding of planetary formation, planetary system habitability, and the distribution of organic chemistry throughout the galaxy. Nations that develop the ability to detect these objects early and to position spacecraft to intercept and study them would gain unprecedented insight into how the universe operates at the scale of planetary systems. The race to understand these visitors is becoming, in many ways, a race to understand our cosmic origins and our cosmic context. It's a race being conducted without formal frameworks or international agreements. Nations are positioning their telescopes, their spacecraft, and their scientists to ensure they're first to the next discovery. What Webb revealed about 3I Atlas is that the universe is far more chemically connected than most people realize. The comet carried a message in its isotopic signatures, in its molecular composition, in the frozen ices that survived a journey through the void. The message is that the chemical building blocks of life are not confined to one special world orbiting one special star. They are produced in stellar nurseries and carried between worlds by objects that traverse the interstellar medium. They accumulate in planetary systems and create the chemical foundation upon which life can potentially emerge. Earth is not unique in receiving this gift. It's unique, perhaps, only in being a world where life actually took hold and flourished. The question Webb's observations have crystallized is whether Earth's uniqueness is a reflection of cosmic rarity or cosmic probability. The comet will continue its journey outward, moving away from the sun, carrying its ancient secrets back into the void. Additional observations are scheduled for the coming months as it recedes. The Perseverance rover on Mars recorded observations. Lucy, the spacecraft designed to study asteroids, captured images. Stereo, Maven, MRO, Spherex, and others contributed to a comprehensive portrait of this ancient visitor. What will emerge from this cascade of data is still being synthesized, but the implications are becoming clear. We live in a galaxy where the chemistry of life is actively distributed between worlds. We live in a universe where the building blocks of biology are not accidents, but inevitable consequences of stellar and galactic evolution. We live in a cosmic context where the question is no longer whether the building blocks of life exist elsewhere. The question is, given that they do, how many worlds will use those building blocks to actually create life? How many inhabited worlds exist in the regions of space from which this comet originated? How many civilizations have emerged in those distant stellar nurseries, perhaps now billions of years beyond Earth's technological civilization? And most troublingly, if these visitors carry the chemistry that permits life's emergence, what else might they carry? The data keeps accumulating. The research papers keep appearing. In June 2026, with the publication of the comprehensive Nature paper detailing Webb's findings, the scientific community reached a consensus. 3I Atlas represents a fundamental shift in our understanding of prebiotic chemistry's ubiquity in the galaxy. But consensus in science is not the same as closure. It's actually the beginning of deeper investigation. Astronomers are now hunting for more interstellar objects. They're developing detection algorithms that could identify visitors still in the outer solar system, objects we haven't yet discovered. They're planning missions that could intercept future comets and return samples to Earth. They're asking whether the interstellar medium itself carries organic molecules, whether the space between stars is suffused with the chemistry of life. What most people don't understand is that this discovery reframes the entire question of life's rarity or commonality in the universe. For decades, scientists debated the Fermi paradox. If the universe is vast and old, why haven't we detected alien civilizations? The traditional answer was that intelligent life must be extraordinarily rare. But if the building blocks of life are being continuously seeded throughout the galaxy by interstellar objects, if multiple star systems are receiving bombardments of prebiotic chemistry, then the question becomes not why intelligent life is rare, but why intelligent life is not everywhere. The absence of detected signals from alien civilizations becomes harder to explain if the chemical foundations for life are ubiquitous. Either intelligent civilizations arise frequently but choose not to broadcast signals, or they arise and destroy themselves, or something else is happening that our current frameworks don't account for. The comet's path forward raises questions that extend into pure speculation. Will it ever encounter another star system? When it does, will it deliver its cargo of prebiotic chemistry to worlds that harbor early life, accelerating evolutionary pathways? Will it seed worlds that develop intelligent civilizations and eventually create their own technological observers? The comet exists on a temporal and spatial scale that makes such questions almost meaningless, but they highlight the fundamental mystery that 3I Atlas has brought to our doorstep. Life, it appears, is not confined by the boundaries of single star systems. The chemistry that permits life is actively transported between worlds. The universe is not a collection of isolated planetary systems. It's an interconnected network through which ancient chemical blueprints travel on billion-year journeys between countless worlds. What emerges from this realization is a cosmos far more biological, far more chemical, far more fertile, with possibility than we had assumed. And we're only beginning to recognize what that means. The comet is gone now, moving back into interstellar space. But the questions it has left behind will occupy astronomers, astrobiologists, and theorists for generations to come. What else might be traveling between the stars? What other secrets are being carried toward us, toward every world, on these ancient messengers from the early universe? And most crucially, if the chemistry of life is this common, this distributed, this inevitable, then where is everybody?